Okay, in this video we are going to talk about graph decomposition. Okay, so graph decomposition is a well studied topic in graph theory, and today we are going to discuss only the basic definition of graph decomposition. So let's consider this graph. Okay, so let's consider this graph G, and here the graph decomposition is take this graph and decompose this graph into smaller graphs, subgraphs, in such a way that the edges are disjoint. For example, if you take this graph, okay, what we could do is we could take this graph and decompose into a 4 cycle that corresponds to this portion of this graph, okay, a C4, okay, then this triangle and this path, a path on 2 vertices or P1, okay, and here we can see that the edges are disjoint. Okay, so the graph decomposition means take a graph and in this case we decompose into, okay, a 4 cycle, a 3 cycle and a path on 2 vertices P1. Okay, and the most important thing is that in order for a decomposition to be valid, okay, there must be edge disjoint. Okay, so okay, so if you look into this decomposition, we can see that we have a 4 cycle, a 3 cycle and a path on 2 vertices, and okay, these 3 subgraphs are edge disjoint. We can see that, okay, no edges in common, so this edge corresponds to this one, okay, this corresponds to this and so forth. So this C4, it corresponds to this portion of this graph, and this triangle corresponds to this portion, and this path corresponds to this portion. So here we decompose the graph into a 4 cycle, a 3 cycle and P1. Anyway, this is okay, this is not the only way to decompose a graph. Okay, you could decompose into something like, okay, a path, then another path, then a triangle and a path. Okay, so we could decompose a graph into many subgraphs, and here the most important thing is that all the subgraphs must be edge disjoint subgraphs of G. And also if you take the union of the edge set of all these subgraphs, then we must get the edge set of the original graph. Okay, so that's what graph decomposition is. Okay, decompose a graph into subgraphs in such a way that the subgraphs are edge disjoint. Okay, subgraphs are edge disjoint. So let me give the generalized definition of graph decomposition. So a decomposition of a graph G is a family. Okay, let's call that family F of edge disjoint subgraphs of G such that So if you take the union of all subgraphs belonging to that family, and if you do this, okay, so take the head set corresponding to, okay, each member of the family, take the union, okay, then you must get the head set corresponding to the original graph. Okay, so a decomposition of a graph G is a family of adjacent subgraphs. So family is represented by this F. So this F will contains its members like F1, F2, F3, etc. And said that, okay, if you take the union of that says corresponding to the member of the family, okay, the members of the family, then you must get the head set corresponding to the original graph. Okay, and here this adjacent means if you take the intersection of the head set of the members of the family, okay, E of F, you must get the empty set. Okay, that's what adjacent means. So this is how we formally define a graph decomposition. Okay, a decomposition of a graph G is a family F of adjacent subgraphs, such that if you take the union of the member of each member of that family, you get the head set corresponding to the original graph. So in this particular decomposition, here we have three members. Okay, so let's call this F1, F2 and F3. Okay, so here F1 happen to be like C4, a cycle on 4 vertices, and F2 is C3 and F3 is P1, okay, a path on 2 vertices. So here we can see that here our family is nothing but the union of F1. Okay, family contains these three sets, F1, F2 and F3. And again we can see that, okay, if you take the head set corresponding to this subgraph F1 and take the union of that with the head set corresponding to F2, okay, this triangle, okay, union the head set corresponding to F3, okay, this path, okay, we can see that we get the head set corresponding to our original graph G. Okay, so this is a decomposition of this graph G. Okay, so a decomposition of a graph G is a family of adjacent subgraphs such that the union of that set of each member of that family, okay, must be equal to that set of the original graph. Okay, so in this case the graph decomposition consists of these three members, F1, F2, F3, and our family is this set. Okay, and again we can see that this is not the only way to decompose a graph. Okay, we can decompose this graph into a different family. Okay, as I said, something like, okay, this path, okay, this path, then this triangle and this path. That's another possible way of decomposing this graph. Okay, and we can also decompose in a very different way. For example, if you consider this path, okay, this path and a cycle. Okay, and the thing is that the subgraphs must be adjoint, and if you take the union, okay, you must get the head set of the original graph. Okay, so let's consider a special case in which, okay, this family contains only a cycle or a path or something like that. Okay, so that corresponds to what is called a cycle or a path decomposition. So in a cycle decomposition, all the members of that family will be a cycle. So let me give one or two examples, then after that I will give the definition. Okay, so let's consider this graph. Okay, let that graph be say G1. Okay, so in this case we can see that we could decompose this graph into only cycles, which will look something like this. Okay, a C4 and a C3. Okay, so suppose that this is our F1 and F2. So here our family consists of these two subgraphs F2, and again we can say that okay, these two subgraphs are at this joint and it's a valid decomposition. And here the most important thing here is that okay, here okay, this particular decomposition consists of only cycles, and such a decomposition is what is called a cycle decomposition. Okay, so here I think there is only one way for cycle decomposition. Okay, in an arbitrary graph we could have many cycle decompositions. Okay, so this graph has a cycle decomposition. So let's consider a different graph, okay, which looks similar to this, but here we have a structure which looks something like this. Okay, let this be G2. Okay, so here we can see that okay, there is one cycle here, but no way to get a cycle out of this portion, right? Okay, here we have okay, so something like this. So here we have a cycle, and okay, there is no way to get a cycle out of this portion, right? Okay, so this graph doesn't have a cycle decomposition. Okay, but it do have what is called a path decomposition. So we could decompose this particular graph into different paths. Okay, so for example, maybe something like this. Okay, so let's consider this path first. Okay, so we have a path on 1, 2, 3 vertices. Okay, 1, 2, 3. Okay, 4 vertices. A path on 4 vertices, P4. Okay, then we have okay, so this path. Okay, let me use a different color. Okay, so that is a P2, no, P3. Okay, and we have one more path. Okay, if you want, you could consider two different paths. Okay, let me consider this as a single path or something like that. So again we have one more P3. Okay, so here we have a path decomposition for this graph. Okay, this portion, okay, this subgraph and this subgraph. Okay, so this is a path decomposition. Okay, and here okay, if you look into okay, this example, okay, we can see that you can always find a trivial path decomposition for any graph, right? It just lists all the edges of that graph. Okay, for example, if you consider this graph, okay, you can see that okay, you could decompose this graph into paths which look something like this. Consider this edge, consider this edge, like this one, okay, this edge, then this edge, okay, this edge, and okay, this edge. Okay, this is also a path decomposition. Okay, and this kind of path decomposition is what is called a trivial. okay, trivial path decomposition. Okay, here we can see that there is always a trivial path decomposition for any simple graphs. Okay, you can always find a trivial path decomposition for every simple graph. So okay, what you do is, okay, you just list the edges in that graph. Okay, so they are disjoint, and if you take the union, you will get the edge set corresponding to the original graph. Okay, so there is always a trivial path decomposition for every simple graph. Okay, so let me go and give the definition of a cycle or a path decomposition. Okay, so a decomposition is said to be a cycle decomposition if all the members of the family is a cycle. The cycles could be different, but they are all cycles. Similarly, a decomposition is said to be a path decomposition if all the members corresponds to, or all the members are paths. Okay, so if every, so this is the definition of a cycle decomposition. Okay, so every graph of our family F is a cycle. Okay, then the decomposition is called a cycle decomposition. So okay, if you look into this particular graph, so here we can see that we could decompose this graph into these two cycles. Okay, so this corresponds to a cycle decomposition of this graph, but in this case, this graph, it has only a single cycle decomposition. So in general, a graph could have many different cycle decomposition. So if a graph has at least one, then we can have a cycle decomposition for that graph. Okay, so this is an example of a cycle decomposition of this graph. And similarly, if every graph of F is a path, okay, then the decomposition is called a path decomposition. Okay, for example, if you consider, okay, this graph, so this is a path decomposition and this is another path decomposition. So if every member of the family is a path, then that is called a path decomposition. Okay, so let's look into one more example. So let's consider a big graph which looks something like this. Okay, so let's try to decompose this graph into, say, cycles. Okay, so here we can see that, so let's consider, okay, this cycle first. Okay, so if you want, you could consider this outer cycle also. Okay, so here we have this C4, right, and that C4 corresponds to this subgraph. Okay, and we have this subgraph, another cycle. Okay, another C4. Okay, so here our family, okay, it consists of this C4. Okay, then again this C4. Okay, and I think, okay, we could have something like, okay, maybe this cycle. Okay, of C8, 1, 2, 3, 4. 5 6 7 8. Okay, 2 3 4 5 6 7 8. 1 2 3 4 5 6. Okay, 7 8. So we have C8. Okay, and one more subgraph here, which is this triangle. This C3. Okay, so here we can see that, okay, for this graph G, let this graph be G, then this is a cycle decomposition for this graph. Okay, we can see that this is not the only cycle decomposition. Okay, we can have many cycle decompositions here. So if you look into this portion, okay, you can see that we could start with, okay, this cycle, a C5, 1 2 3 4 5. Okay, then a triangle, okay, C4 C5 C3, then maybe, okay, a 1 2 3 4 a C6, and another cycle 1 2 3 4 5 C5. Okay, that is another cycle decomposition. Okay, so here we have this cycle decomposition. Again we can see that if you take the union of all the members of this family and take the edge set of each family, okay, so here this corresponds to C4, this C4, C8 and C3, and if you consider that set of the members of this family, take the union, okay, we can see that you will get the edge set corresponding to the original graph. Okay, so it is a cycle decomposition. Okay, so this graph is to exhibit a cycle decomposition. Okay, one cycle decomposition looks something like this. Okay, and here if you look into this graph it doesn't have a cycle decomposition. Okay, because there is no way to find a cycle out of this portion. Okay. Okay, so in the next video we will prove a condition for which when a graph has a cycle decomposition. Okay, so if you look into this particular graph, you can see that, okay, here we have this vertex of degree 3, this is degree 1 etc., and all other vertices have degree 2, which is even. Okay, but if you look into this graph, you can see that all the vertices have degree even, 1 2 3 4 2 2 2 2 1 2 3 4 5 6 2 2 1 2 3 4 4 2 2 2 etc. Okay, so it seems like if all the vertices have even degree, then there exists a cycle decomposition. Okay, at least from this example we can see that in this case, this graph, all the vertices have even degree, whereas if you consider this particular graph, we can see that here we have this vertex. Okay, anyway, 3 vertices of degree 3. The thing is that here we are considering these cycles, right? Okay, so similarly, okay, here one more, this vertex do have degree 3. So we can see that if we consider a particular vertex and a cycle, okay, one edge come to that vertex and another edge will leave that vertex, right? You know, so in order for something like this, suppose that we have this vertex, and suppose that this vertex is a part of, say, two cycles or something like that. So first cycle comes in and goes through a different edge. Similarly, when considering the second one, it must come from a different edge and leave through a different edge, something like that. So it seems like, okay, if the degree of each vertex is even, then we can find these kind of cycles. Okay, anyway, in the next video we will go and prove that theorem. Okay.